Okay, so today we are naming and writing reactions for carboxylic acids and esters, and this is our last lecture of the elementary organic part. After this, we begin the biochem half of the semester. So we're going to do this week focusing on carboxylic acids and esters. And again, we're focusing on this from an elementary organic standpoint. So if you're watching this video as a organic student, the way you talk about carboxylic acids and esters in organic chem is going to be at a deeper level than the way we would look at them at the elementary organic level. So just a word to the wise there. So when we talk about carboxylic acids and esters, they're analogous to aldehydes and ketones in the sense of, remember aldehydes were at the end of the chain, right? Well, a carboxylic acid is also at the end. And a ketone is in the middle, right? Well, an ester is in the middle, right? So aldehydes are carboxylic acid analogs, and ketones are esters analogs, right, in terms of where they're located. So when we're looking at molecules containing carboxylic acids versus molecules containing esters, right, a carboxylic acids are going to be on the end, just like an aldehyde is going to be on the end, and an ester is going to be on the interior, just like a ketone is going to be on the interior. Right, so they are analogous to each other in that regard. And so let's look at just carboxylic acids first. We write out the carboxyl group as C double bond O OH. So you might see it written out as COOH, or some books even write it as CO2H, right? A lot of students misidentify this. If I say, what functional group is this? They'll say, oh, it's I don't know, a ketone and an alcohol. But that's not correct, right? When these two are together, that is one functional group called the carboxyl group, or the carboxylic acid group. Okay, that's why it's COOH or CO2H. They're very, very, very polar. Right? If we think back to our intermolecular forces, you've got dipole-dipole coming from this piece right here, and you've got hydrogen bonding coming from this piece right here. So in terms of their boiling points, would you expect them to be high or low? Very high, right? They're going to be even higher than alcohols and amines. So far, those are the highest boiling points we've seen this semester, right? Alcohols and amines have hydrogen bonding. Well, a carboxylic acid has hydrogen bonding as well, but it also has dipole-dipole. So it's like the king in terms of who's going to have the highest boiling point. If we have 3 or 4 molecules of all similar sizes, of course, right? One of them can't be part of a 20 carbon chain and the other part of a 3 carbon chain. That wouldn't be fair. But if they're all similar sizes, one's an alcohol, one's an amine, one's a carboxylic acid, and I said, who's the highest? The carboxylic acid is going to boil higher than both the alcohol and the amine. And so here are some data. Right, so here's butane, wimpy little butane, boiling point of -0.5 gas at room temperature. There's an ether, right? We said ethers have a very weak dipole-dipole, very weak. Notice it only brought you up 7 degrees, or 6.5. 7.5, I mean. Then we jump up a good bit when we get to the aldehydes and the ketones, right? There's an aldehyde at 49. There's a ketone at 56. It's a significant jump from here. And there's a significant difference between these two, right? And then you jump again when you get the alcohol involved, 1 propanol. And then when you get the carboxylic acid involved, you get a big jump too, right? So all 3, hydrogen bonding, dipole-dipole, weak dipole-dipole, and then London only. And again, just like solubility of all the other ones we've seen, that chain length needs to be 6 or less. Why is 6 the magic number? Because after 6, when this chain gets to be too long, what happens? It becomes too nonpolar, right? The nonpolar component can't be outweighed by the polar component. Right? Because this is the polar component here. This is where all the hydrogen bonding is taking place. If this chain gets to be too long, well, now this chain is not capable of hydrogen bonding. So now it becomes a barrier to solubility, right? Because this piece down here is too nonpolar to offset the polar part. And this figure's in your book, right? So methanoic, ethanoic, propanoic, butanoic, pentanoic, where yes. At butanoic, we start getting slightly, and then after that, it would be insoluble.
So is the OIC the suffix?
Yep, we're going to talk about that in just a second. Just want to throw this out here now because we'll see this in the biochem section when we start next week. When we have a carboxylic acid with a big long chain, right, so greater than 10 usually is where we start calling it a long chain, we call those fatty acids. And that's going to be a big part of what we're talking about next week in biochem. That's the first biomolecule we'll look at, are fatty acids. So just throwing that out here. Right? This is what we're talking about. Carboxyl group with a big long chain, we call those fatty acids. And that's where we're going to start the biochem section, is with this, since we're leading off with it, I mean, since we're finishing this week. So how do we name a carboxylic acid? It's pretty easy. By definition, the carboxyl carbon is number 1. Just like when we named aldehydes, right? The aldehyde carbon was number 1 by default. Why? Because the aldehyde's on the end. We're only naming molecules with one functional group, so we don't need to worry about, multiple functional groups going on. So by default, the carboxyl carbon's number 1. Then if we have any substituents, we would locate them, put them with numbers, so 2-chloro or 4-methyl or whatever, right? And then your suffix is oic acid. So if you had this molecule, right, here's carbon number 1. A lot of students misidentify the length of the chain. For some reason, they want to call this carbon 1, but that's not a carbon, right? That's an oxygen atom. So the carboxyl carbon, the carbon that has the COOH, excuse me, that's carbon number 1. So 1, 2, 3, 4. So 3 bromo, and then this is a 4-carbon chain, butanoic acid. Easy enough? It's basically the same as naming aldehydes, right? It's just a different suffix. So I'll pause the video and give you a chance to try naming these two. All right, let's name these two molecules. So when we're naming these two, picking carbon number 1 doesn't take a whole lot of effort, right? Because all we need to do is find the carboxyl group. So we're going to name from the left or from the right? From the right. So 1, 2, 3, 4, 5, 6, 7, 8. All right? And so what are our substituents? So it would be what numbers?
4, 7.
Right, 4, 7. Dibromo, right? Then what? 5 ethyl. And then what?
Is it octanoic?
Octanoic acid. And then here, again, carbon number 1's easy. 1, 2, 3, 4, 5, 6, or 5, 6, 7. We have 7 carbons, right? 5, 6, 7. So what's the name of this?
4,
5 dimethyl, right? And this is a 7-carbon chain. Hexanoic acid, right? Good. Do we feel good about naming these? So no worse than naming aldehydes, right? In terms of locating carbon number 1, it's going to be the one with the functional group. And then all you need to do is worry about any substituents you might have. And obviously your parent chain, just pick the longest one, right? Okay, I'm going to let you try these. Go. I'll pause the video and let you try these. All right, let's look at what we've got here. Hexanoic acid would be how many carbons? 6. That's a 6-carbon chain. So 1, 2, 3, 4, 5, 6. And now you can choose carbon number 1, whichever end you prefer, right? So let's just make number 1 over here. Okay, so 3, 3, 5 trimethyl. So 1, 2, 3, 3, 3, 4, 5, 5 trimethyl, and then 2-chloro. So there's that one. And then this one's also a hexanoic acid. So 1, 2, 3, 4, 5, 6. Just for fun, let's put carbon number 1 over here this time. 2,3-diethyl. So 1, 2, and then 3. So 2,3-diethyl hexanoic acid. 3,3,5-trimethyl 2-chloro-hexanoic acid. Feel good on these? We're good on those.
Why is there a line between fluoro and hexanoic?
There shouldn't be a dash right there. You're right. There shouldn't be a dash right there. It should be continuous. 2-chloro-hexanoic acid. Yeah, that's just a typo. There should not be a dash there. Good catch. Okay, so when we have 2 carboxyl groups, we call that a dioic acid. Just like when we had 2 aldehydes, we called that a dial, right? If we have 2 carboxyls, that would be a dioic acid. And it's not butadioic acid, it's just butane dioic acid. Okay, so you don't change the parent at all. You just call it butane dioic acid. Okay, so this is a 4-carbon chain, 1, 2, 3, 4, or 1, 2, 3, 4. It really doesn't matter here, right? Because there's no substituents. So this would just be called butane dioic acid. And then if there were substituents, right, let's pretend there was a chlorine right here. That would be 2-chloro-butane dioic acid. Okay, make sense? And if we're talking about aromatic, right, so if the parent molecule is a benzene ring, then we would call that benzoic acid, right? And then we would have any other substituents on there, just like we've already talked about. So for instance, if you had this, right? You could name this what? You could name it 2-bromo, and then the parent molecule is benzoic acid, right? Or what's the relationship when they're next door to each other?
Oh, it's an L.
Oh, right. Or you could say O-bromo, benzoic acid. See what I'm talking about there, right? This is the parent molecule. And then any substituents, or maybe, you know, it was over here, that would be M, or over here, it would be P, right? So when it's on a benzene ring, that's the only aromatic that you're gonna have to worry about in this class. Because the only aromatic molecule we dealt with at any level is a substituted benzene, right? There are lots of aromatic molecules that exist, but the only one we look at in elementary organic is benzene, substituted benzenes. Right, so there would be benzoic acid. You could name this 4-amino-benzoic acid or p-amino-benzoic acid, right? What if you had 2 substituents? Well, you couldn't use the meta-ortho-para, right, because that only works if there's 1 substituent. But you could just call it 3,4-dichloro-benzoic acid. So you might see some of those on the homework sets. This is one I just drew, so I won't pause the video. Right, that's 2-bromo-benzoic acid. Should have thought before I drew. Now, when we make carboxylic acids, how do you make a carboxylic acid? Well, you can oxidize an alcohol into an aldehyde, right? And then you can take that aldehyde and further oxidize it into a carboxylic acid, right? So last week, we did this step. We learned how to take an aldehyde and make it into a carboxylic acid. And I said, well, you don't know how to name it yet. Well, now you do, right? You take your aldehyde and you turn it into a carboxylic acid, right? Because I told you aldehydes are super easily oxidized. That'll happen just sitting out on the shelf in your lab area, right? So aldehyde is easily oxidized to a carboxylic acid. And how could you make an aldehyde? Beginning with an alcohol, right? So ethanol to ethanal, ethanol to ethanoic acid. Right? And this is an easy process. You would not have to use a strong oxidizer to do that. So for instance, if I wanted to make butanoic acid, what alcohol should I use? Not what aldehyde, what alcohol. Taking it back 2 steps. If I'm trying to make butanoic acid, what alcohol should I begin with? So let's work backwards. If I want to make butanoic acid, let's draw it out. 1, 2, 3, 4. What aldehyde did butanoic acid come from? What got oxidized to give me this carboxylic acid? Butanal, right? 1, 2, 3, 4. Right? That's butanal. And what alcohol got oxidized to give me butanal? Where was the alcohol located, in other words? Right, so that would have come from what alcohol? 1, 2, 3, 4. Let me just draw it, stick it down. It would have come from 1 butanol, right? It couldn't have come from 2 butanol, because that would have given me a ketone, right? It had to come from 1 butanol. If you oxidize 1 butanol, you'd get butanal, right? If you oxidize 2 butanol, you would have gotten a ketone. You would not have gotten an aldehyde. You see what I'm asking now? So if we've got propanoic acid, prop is 3. 1, 2, 3. What aldehyde was oxidized in order to make that? Propanal, right? 1, 2, 3. And then I asked you which alcohol this came from. So what alcohol did that come from? Propanol, right? Do you see how we figured that out? You just work backwards. The main thing to think about when you're naming your alcohol is you need to number where it is. So is it propanol or is it 1 propanol? That's right. Because if I had 2 propanol, would that have given me propanal? No, that would have given me a ketone, right, when I oxidize it. So just be careful. You don't need the number on the aldehyde, but you will need it on the alcohol, since alcohol can be anywhere. Does that make sense? So if you get asked something like that on the homework, just walk yourself back 2 steps. Okay, the aldehyde that made this carboxylic acid, and then the alcohol, which would have been used to make that aldehyde. Carboxylic acids are weak acids. So if you remember back to Gen Chem 2, they have weak acid properties. They do not fully dissociate. They have Kas less than 1, weak acids. These are not strong acids. They're not like nitric acid or hydrochloric acid, right? These are weak acids that don't fully dissociate. And the next time you're looking at something highly processed, you might see some carboxyl salts as preservatives. That's what helps give these things like indefinite shelf life. These are all parts of, your average college student's diet, right? Sodium acetate, you'll see that as a preservative. Also helps give it that shelf life that'll last forever and ever and ever and ever and ever. Now here's a reaction that we need to know. It's called the esterification reaction. Esterification. So this is the reaction between a carboxylic acid and an alcohol. It requires acid as a catalyst, and it gives us an ester and water. Okay? You get an ester and water. And this is the generic form of it. This is the generic form. Oh, my clock's battery died. I'm just noticing that. I'm going to have to find a way to keep up with the time. Okay, carboxylic acid and alcohol gives us an ester and water. So this is the generic reaction. So I'm going to smush this down. I don't know what that's doing there. Let's make this like 40. Put it up here so that I can write. Okay, so let's do an example. So R here is just whatever the chain is, right? And R here is just whatever the chain is. So let's use, I don't know, let's do a 4-carbon chain. So 1, 2, 3, 4. Right, so that would be butanoic acid. Right? And for the alcohol, let's do a 3-carbon chain. So it would need to be a primary alcohol, just for simplicity's sake. So let's do 3-carbon chain, so 1 propanol. Right, 1, 2, 3, and 1, 2, 3, 4. So what you're going to get, now again, remember, we're only looking at the overall reaction in elementary organic chem. We're not looking at the mechanism and how many steps this occurs in and all that good stuff. You'll deal with that in organic too. But in elementary organic, we're just looking at the net picture, the overall reaction. Okay? So we need our catalyst. And what we're going to get is the carboxyl part and its chain. Just redraw it. 1, 2, 3, 4. Okay? And then we're going to get an ester formed. So this H and this OH, that comes off as water. So our other product is water. That's where it's coming from. And then this O, and then whatever its chain is. 1, 2, 3. Okay? So there's your ester and there's your water. Do you see how we did that? Now again, we're not getting into the nuts and bolts of how it happens and how many steps it happens in. We're just looking at the big picture, the net reaction. So this is called esterification because you're making an ester. Right? This is your ester. We'll learn how to name esters in just a second. Acid is the catalyst, and this reaction actually is reversible. That's why it's got the double-headed arrow there. It's an equilibrium reaction. And water is your second product. So whatever this R is, that stays attached to the carbonyl. And then whatever this R is, that stays attached to the O. And then those two make your ester, and then your R groups are just off the sides. Make sense? And so that's why we can generalize it with, you know, R or X or whatever variable you want to use. So there's one I just talked about. Let's try this one. I'll give you a second to try this. We don't know how to name the product yet, but I'm going to pause it and let you try. All right, let's go over this. So, what are we going to get? 1, 2, 3, 4, 5. So we're just going to redraw that, right? 1, 2, 3, 4, 5. Oh, that's a funky angle. 5. There's our carbonyl, right? Now, this and this are going to come off as what? Water, right? So that's our other product. And then what's going to be left? 1, 2, 3, 4. So we need to draw O. 1, 2, 3, 4. Do we agree?
Yeah, so after the water comes off, it's just everything that's left.
Right. O and then whatever's on that chain. Does that make sense? And again, we're not looking at the details of how the reaction happens. We're just looking at the big picture, overall net reaction. Make sense? And we'll learn how to name this ester in just a second. I think I've got another one in here for you to try. Yes, I do. So I'll pause it, give you a chance to try this one. All right, let's look at what we got for this one. So we have 1, 2, 3, 4, 5, 6. Right? So 1, 2, 3, 4, 5, 6. And then we're going to have O. And then how many carbons are on the other side of the chain? 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. Yeah, that's right. And then what's our other product? Plus water. Right? Got to obey the law of conservation of mass. Do we understand how this works? Feeling good about esterification? Right? It's an alcohol and an ester. Acid catalyst. And it is technically reversible. We're not getting into the mechanism or anything about how the reaction takes place. We're just looking at the big picture in elementary organic. Okay, so now let's talk about esters. Since we made esters, let's talk about them now. So, like I said, in an ester, that H is gone, right? Because a carboxylic acid is COOH, so an ester is just COO, right? And it's on the interior of a molecule. So a carboxylic acid has to be on the end, right? Because hydrogen can only form one bond. It's not like you can have the chain continuing on the other side of a hydrogen, right? Hydrogen stops the chain. Whereas an ester, because there's no hydrogen, it's on the interior. So it can have anything on that side, anything on this side. So could this even be a ring? Could these two be looped around to each other, make a ring? Yeah, yeah. Just like you can have a ketone in a ring, right? You can't have an aldehyde in a ring unless it's sticking off the ring somehow. You can't have a carboxylic acid in a ring, right, unless it's sticking off. But you can have an ester inside a ring because who cares if these two are bonded to each other, right? That's not going to affect the ester. Esters generally smell pretty good. That's a picture from your textbook. So a lot of these esters you actually see as things that we like oils, you know, used as fragrances and that sort of thing. Banana oil, pineapple, raspberry, oranges, etc. Right? They're not highly stinky like thiols. The SH functional group is something you run from. It really stinks. But the esters, those generally smell pretty good. Also, aspirin contains an ester, right? There's the ester in aspirin. And then there's another ester. You may have seen, you know, in like your products that are tingly and help with your muscles. Okay, now because they are on the interior, their boiling point isn't going to be as high as a carboxylic acid. But would an ester's boiling point be higher than a ketone's? Yes, that extra oxygen will make it more polar, right? But it's not going to be a humongous difference. It's going to be higher, but it's not going to be like 50 degrees higher, right? You will notice a difference, but it's not going to be humongous. Like an aldehyde versus an alcohol kind of thing. So here is a figure from your textbook. I wish it would have put an aldehyde in there just as comparison, but it didn't. Oh well. Right, there's butane. I always pick on poor butane. There's the ether analog. There's the ester analog. Right? There's the alcohol analog, and then there's the carboxyl analog. Right? And so when we name esters, this is why we talked about esterification, because the way we name esters is based on how the ester was made. So if you're looking at an ester, you kind of have to break it down. You need to name the part that came from the alcohol first, In other words, what side is attached to the O? Remember when we just drew esters a few minutes ago? It was carboxyl, O, blah, 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 right? The O, blah, 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 that comes first. And then the part that came from the carboxylic acid, in other words, the part that's attached to the carbonyl, goes second with a suffix OATE. Now I could flip it around 180 degrees, right? If I take that molecule and rotate it, you would still need to identify the part that came from the alcohol and name it first, and the part that came from the carboxyl and name it second. Okay, so don't let that throw you off. All the ones we've done so far have had carbonyl, then O, right? But what if I had O, then carbonyl? You would have this part first, as opposed to this part first. So if I take a molecule and rotate it, just to see if you're paying attention, right? Watch out for that kind of little trick. So here's an example, right? This is the carbonyl carbon, and this is an ethyl. Now watch out. A lot of students make this mistake, so please don't do it. Don't forget to count the carbonyl carbon as part of this chain, right? It's ethyl. A lot of students would say that that's methyl, but it's not, right? That carbonyl carbon does count as one of the carbons in the chain. So this is ethyl, and then this part right here is methyl, right? That's not a carbon, that's an oxygen. So this would be methyl ethanoate. Does that make sense? This part came from the alcohol, this part came from the carboxylic acid. So methyl ethanoate. If I gave you this molecule and said, okay, how would you synthesize it? You could break it down, right? This part came from methanol, this part came from the carboxylic acid. And again, this is an example where it's been flipped, right? All the ones we've seen so far have had the carboxyl first and the O second, right? But we took it and we flipped it. O first, carboxyl second. This part came from methanol. This part came from ethanoic acid. Make sense? Okay, so name this, and then just for good practice, identify which alcohol and which carboxylic acid it came from. I'll pause it and give you a chance to try that. All right, let's look at this one, see what we got. So when we break this down, what part did this come from? The carboxylic acid or the alcohol? All right, this came from the carboxylic acid. What carboxylic acid specifically did it come from? Right, this came from ethanoic acid. And what part did this come from? That's the alcohol piece, right? It came from what alcohol? 1, 2, 3. Propanol? Do we just leave it like that? 1 propanol, right. So what's the name? Do you put the alcohol component first or the carboxylic acid component first? Okay, so what would the name be when we take this? Okay, so we break it down. Oops, I moved it on the screen. Propyl, ethyl, propyl, because that's from the propanol, and then ethanoate. I moved this picture so I could write on the board easier. So this is from 1 propanol, right? So it'd be propyl. And then this is the new parent chain, so to say. And then the subscript, and that subscript, the suffix is OAT. Okay, so propyl ethanoate. Does that make sense? I forgot that I moved the slide before I wrote on the screen, so it messed up my PowerPoint. Lost points for flow there. Does it make sense? I think I've got a couple more for you to try. Yes. So name these. And just for practice, let's identify the alcohols they came from as well. I'll pause the recording. All right, let's go over these. So, where do we want to begin? Do you want to start with the alcohol component or the carboxylic component? Okay, that goes first in the name. So what alcohol, what side is the alcohol side? This side, right? So this came from what? Right, came from methanol. You don't need a 1 on methanol, right? Because that's just CH3OH. There's no other place you could put an OH other than carbon 1. And this came from what? 1, 2, 3, 4, right. Utinoic acid. So when you put the two together, what do you get in terms of the name?
Methyl.
Yes, methyl. Butanoate, yes. All right, let's do the next one. Now notice, what's the difference between the A and B?
This side the alcohol's on.
Right, I've just flipped it. Okay, so don't let that throw you off. The carbonyl does not have to come first in terms of reading it from left to right, right? This molecule is perfectly legit. It's just flipped from what we've looked at so far. So where's the part that came from the alcohol? It's now on the left, right? So what alcohol did that come from?
Ethanol.
Right, that came from ethanol. And again, you don't need the 1 on ethanol, because if the OH is here, or if the OH is here, it's still number 1. And then what did this come from? Right, 1, 2, 3. This came from propanoic acid. So the name ends up being what?
Propyl. No. Ethyl.
Ethyl, right.
Propanoate.
Propanoate, good. Good. Do you feel good about how we do this? All right. Oh, I was just showing where I broke it down. Do you want to go through some more, or are you feeling pretty good? Think you got it? Okay. So, right, this one would be butyl pentanoate, 1, 2, 3, 4. That's the butyl pentanoate, 1, 2, 3, 4, 5. All right, that's where the pentanoate comes from. And this would be hexanoate, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I'll give you a second to draw these just for good practice. Ethyl pentanoate and propyl butanoate. Okay, let's draw some esters. So if it's ethyl pentanoate. Let's start by drawing the carboxyl group. I mean, not the carboxyl group, the ester group, and then just figuring out what goes on each side. So what's going to be attached to the O? The ethyl, right. So that's going to be how many carbons? 1, 2, good. And then what's going to be attached here? Now be careful, do I add 5 additional carbons? Would I go 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. No, why not? Because that's a 6-carbon chain, right? This counts as one of the carbons. So technically I'm only adding 4 additional, right? Because this counts as one of them. So 1, 2, 3, 4, right? 1, 2, 3, 4. Oh, there we go, 5. Pent, this counts as one of those. If we're going the other direction for this one, propyl, again, we can start by drawing our functional group. Let's just draw it going this way for fun. So we get used to seeing things from both directions. What's going to be attached to the O? 3 carbons, right? So 1, 2, 3, right? 1, 2, 3. That gives me the propyl. And what's going to be attached to the carbonyl? 3 additional, right? Because that counts as one of them. So 1, 2, 3, 4, right? 1, 2, 3, 4. That gives me the butanoate. Good. Do you feel good about going this way, where I give you the name and you draw it? All right. Okay, now saponification is when we take an ester and we react it with a strong base. So you get your carboxylic acid back, but it's as a salt, okay? In other words, what you're doing is you're getting your ester back in its salt form. Remember if I told you the ester, carboxylic acid salts, right? Well, you can make ester salts as well. So if you take an ester and you react it with a strong base, you'll get your carboxylic acid back as a salt. So you get a carboxyl salt. Go preserve your stuff with that. And you'll get your alcohol. And you need heat to catalyze this. So here's the generic version of it. Okay, this is just a generic version. Here's your ester, where R and R, just whatever the chains are. Now again, we have to be careful about where each piece goes, right? R1 is attached to the carboxyl, so R1 needs to still be attached to the carboxyl, all right? And now it's just sodium whatever, okay? Because we're using sodium hydroxide, so that's where the Na comes from. And then R2, right, stays attached to the alcohol. So basically, we're just reversing what we just had mentioned. So if you have ethyl ethanoate, and you're reacting that with sodium hydroxide, which is a strong base, heating it, you get sodium ethanoate, right, because that's just making the salt analog of it, sodium acetate, in other words, and then ethanol. So you're just undoing that previous reaction that we've done.
So you always NaOH?
Yes, usually. You could use KOH or LiOH as well, but I think your textbook likes to use NaOH. Any strong base, sodium hydroxide, lithium hydroxide, potassium hydroxide would work. So why don't you try this one, saponification of propyl butanoate. We're going to use sodium hydroxide as our base. Okay, let's go through this one. So we've got propyl butanoate. So there's propyl butanoate. Do we agree? And we get sodium propanoate and 1 butanol. Again, that represents heat. All right, the last thing we want to talk about are soaps. So if you take a long chain fatty acid, remember a fatty acid is just a carboxylic acid with a big long chain, right? If you take a carboxylic acid with a big long chain, we call that a fatty acid, and you react it with a strong base, you're going to get a soap, right? In other words, you're going to get a molecule that has a very, very, very non-polar component and a really, really, really polar component. And that's something that we like in terms of cleaning, right? Because if I'm scrubbing grease off of my frying pan, greases are non-polar, right? So grease would dissolve in this, and this polar component can interact with the water, and it can make these little micelles. There's a commercial for some sort of makeup remover right now. It's called micellar water. And I just laugh at the notion because micelles form, right, when you shake up oil and water. They don't, it's not like they're just floating around, those little micelles. If you let that sit, you're going to have an oil component and a water component. You're only going to get your micelles when you shake it up. It does separate, yeah. You should see a big separation. Right, so those micelles will dissolve your nonpolar stuff, and it'll keep it away from the aqueous component, and that's why it can go bye-bye. Right, so this is what it should look like when it's just sitting on your shelf, right? You should see a big separation. You shake it up, you get those micelles, and then all your oils and greases and fats can dissolve because the nonpolar parts are all sticking up. When you force them into interaction with each other, they form those micelles, and that's what's dissolving your oil, right? And it's keeping it away from the water so you can wash it off. So it's very convenient. And so that's what we use when we want to get something non-polar clean using a polar solvent like water. And so there's another picture from another textbook, right, from hydrophilic and hydrophobic. And then there's another picture from another textbook as well. And that's a lab that we do. We actually make a soap using vegetable oil. It's obviously not going to be as good as your commercial stuff. So that's where we're going to stop. And do you have any questions for me? And that's where we will stop.